Hello, this is John Miyares, and in this lesson, we are going to talk about ellipses. Some of you have probably heard of ellipses, the idea that planets travel in elliptical orbit around the sun rather than in a circular orbit, and there will be some applications that we're going to cover here. But the focus of this lesson will be similar to what we did with circles, where we looked at the properties of the shape, looked at a general form of the equation, then looked at two types of problems. One, where we started with the equation and we had to find the properties and sketch the graph, or two, given the properties of the graph, determine the equation. If you've looked ahead at the other sections of Chapter 11, you're going to see other shapes known as conic sections that we'll be working with, such as parabolas and hyperbolas. In sections 11.1 through 11.3, the textbook author focuses on the most basic of these shapes, all centered at the origin, while in section 11.4, they take all of those conic sections and look at them in a single section of homework, but where none of them are centered at the origin. What I'm going to do here is teach you all how to work with ellipses in any form, whether they are centered at the origin or not. This way, we're covering all of section 11.2, then part of section 11.4. When we cover hyperbolas in section 11.3, we'll do the same thing where we will look at them centered at the origin in section 11.3, then look at them centered elsewhere in section 11.4. So now you might be asking yourself, why am I teaching things in this order if the textbook author didn't write them in this order? Well, you're going to learn pretty quickly that I don't have a lot of respect for this textbook author, but I do believe in teaching you all the content in a way that will ultimately make sense and minimize stress. Now, be warned right off the bat that although we're going to talk about one idea, like ellipses, there's a lot of pieces that have to get taken into consideration, and some of this may come kind of fast. Remember, you have two things that can help you as you're going through this. First, you can pause and rewind this video if you need to listen to something again, or if you have a question that comes up that the lecturer can't answer, jot it down so that you don't forget it, so that when you come into class next time, you can ask it. Or if you don't want to forget the question, you can always send it to me via email, or better yet, post it on a discussion board. With that in mind, let's get started. So what is an ellipse? So our formal definition is given here. An ellipse is the set of all points on a plane, the sum of whose distances from two fixed points known as the foci or focal points is constant. The center of an ellipse is going to be the midpoint of the segment between these two foci. So you can basically see what's going on in this diagram is we have an ellipse, kind of looks like a circle, but it's not perfectly round. And instead of having a constant radius, you have a variable radius all the way around. In this drawing, going from the center and heading out left and right, you have what I'm calling the horizontal radius, which in this case is as long as the radius of this object can be. And going up and down from the center is what I call the vertical radius, which is as short as the radius can be. The points marked at C and at negative C are called the focal points or the foci. And if you were to draw segments from those focal points to any point on the outside of the ellipse, then the sum of those distances, here labeled D1 and D2, would be a constant. And that constant would be the length of what we call the major axis or the long diameter. This slide will hopefully demonstrate the differences between circles and ellipses. In a circle, you have a single center point and one distance, the radius, that is constant all the way around. So you could construct a circle by pinning a string tied to a pencil on a piece of paper, then drawing all the way around. In an ellipse, you still have a string of fixed length, but the endpoints of the string are pinned down in two places. Those two push pins you see here represent the foci or focal points. And when you go all the way around with your pencil like that, the sum of the distances from each focal point to the points on the ellipse add up to be a constant value. Now let's talk about the properties of an ellipse. Like a circle, an ellipse has a center point, but unlike a circle, you have this long diameter and a short diameter. The long diameter is called the major axis, and the short diameter is called the minor axis. The vertices of the ellipse are at the end points of the major axis, while the points at the end of the minor axis are called covertices. The focal points, marked here as F1 and F2, are always going to be on the major axis. Now, of course, the major axis doesn't have to be horizontal. It could be vertical, like in this picture here at the bottom of the screen. Now, I'm going to introduce some terminology that isn't necessarily in the textbook, but I'm going to use this terminology to help put things into context. The first term I'm going to introduce here is something called the horizontal radius. The idea is that the length of the segment which runs horizontally from the center to the outside of the ellipse, either directly to the right or directly to the left. Similarly, the vertical radius is a segment which will run from the center point vertically to the outside of the ellipse, either straight up or straight down. In both of these figures, I have them labeled with a value A being the horizontal radius and B being the vertical radius. Now, other books will refer to these lengths as the semi-major axis and the semi-minor axis. These essentially just mean it's half of the major axis and half of the minor axis. And I suppose technically calling them the semi-major axis or the semi-minor axis would be more appropriate to use. However, our textbook doesn't use those terms either. The problem with using those terms is that the semi-major axis is sometimes horizontal and sometimes it's vertical. Whereas in the approach we will use, the horizontal radius will always be horizontal and the vertical radius will always be vertical. Similarly, to simplify matters, my horizontal radius will always be labeled with the letter A, and my vertical radius will always be labeled with the letter B. The general equation of an ellipse, when you look at it, resembles the equation of a circle a lot. You have the x minus h squared and the y minus k squared terms, just like in a circle. But now they're divided by these terms a squared and b squared, and the whole thing adds up to equal 1. In this case, the a squared term in the denominator is going to be the horizontal radius squared, while the b term in the second denominator is going to represent the vertical radius squared. How can I remember which is which? Well, a always comes before B, just like X comes before Y in the alphabet. Similarly, when you graph things, the X values are always measured horizontally, while the Y values are always measured vertically. So the A term will always be below the X because X is horizontal, and the B term will always be below the Y because B and Y are both vertical. Now, to simplify matters for most of you, we're going to just use this one formula to describe the ellipse, whether the major axis is horizontal or vertical. The textbook actually gives two equations because it wants the a value to not be the horizontal radius, but it wants the a value to be the length of the semi-major axis, and then the b value won't always be vertical, but the b value would be the length of the semi-minor axis. And then you'd have to flip them around when the major axis is vertical. Personally, I'm not a fan of memorizing two different formulas for the same shape when one is going to do just fine. So we're going to work with just one formula here and say whichever of the two is bigger, either the A or the B, is going to be the major axis. The foci of an ellipse, as I mentioned before, will always be on the major axis and will always be a distance of c units from the center of the ellipse. We also have a formula to compute the length of c, which can be simply put as the semi-major axis squared minus the semi-minor axis squared. For those of you who prefer simpler formulas, it's either going to be c squared equals a squared minus b squared, or c squared equals b squared minus a squared, depending upon which difference will give you a positive number. We also have this property of the ellipse called the eccentricity, which, simply put, is a measure of the roundness of the ellipse. It is computed by calculating this value c, the distance from the center to the focal points, and dividing it by the length of the semi-major axis, which could be a if it's horizontal or b if it's vertical. Possible values of the eccentricity can range from 0 to 1, where e values of 0 make the ellipse look more circular, and values of e close to 1 will make the ellipse look long and skinny, like a hot dog. On a test, you probably will not have to do anything involving eccentricity, but on the homework, there are some questions on it, which is why we're going to introduce it here. Here's our first example. Find the center, vertices, foci, and eccentricity of the ellipse with the given equation, then sketch its graph. Now, honestly, I might recommend not answering all of the pieces of this problem in that order. What I would probably do is identify the center, the horizontal radius, and the vertical radius, then sketch the graph, and then answer the questions. So let's try that. Our equation is x minus 1 quantity squared divided by 9 plus y plus 2 quantity squared divided by 4 equals 1. The horizontal radius is going to be taken from the square root of the denominator of the x terms, which will be the square root of 9, or 3. The vertical radius will be the square root of the denominator of the y terms, which is the square root of 4, or 2. Since the horizontal radius is larger than the vertical radius, then the major axis will be horizontal, which means our vertices are going to be 3 units to the left and right of center, and our focal points, after we calculate a value for c, will be c units left or right of center. The center can be found just like we found in a circle by looking at the values being subtracted from the x and y in the parentheses. So that is going to be the point 1, negative 2. In sketching this graph, we'll first set up our axes and plot our center point. The center point, as we said, is at 1, negative 2. Next, we know the horizontal radius is 3. So we're going to plot a point 3 units to the left and 3 units to the right of center, which puts us at negative 2, negative 2, and 4, negative 2. Next, we'll plot the co-vertices, which are going to be 2 units above and 2 units below the center point, which will then be the point 1, 0 and 1, negative 4. Finally, we'll sketch our ellipse through those 4 given points. So other questions you might be asked on a homework problem would be the length of the major axis and the minor axis. These will be 6 and 4, respectively. The major axis can almost be thought of as a long diameter, while the minor axis can be thought of as a short diameter. The vertices are going to be at the endpoints of the major axis. And since the major axis is horizontal, they can be found by adding or subtracting 3 from the x-coordinates of the center point as seen here. The homework problems in this book don't worry so much about the covertices, so they can be ignored. Next, we want to find the focal points, so we need to compute the value of C. To do this, we need to take the length of the semi-major axis squared minus the length of the semi-minor axis squared, then take the square root of that result, which will be 9 minus 4, or 5. Since the focal points are always on the major axis, we can add or subtract the square root of 5 from the x-coordinate of the center to get the focal point locations, which are shown here. Finally, for the eccentricity, we're going to have to divide C, the square root of 5, by the length of the semi-major axis, which is 3, to get this ratio as the square root of 5 over 3. Here is a very similar example, except this time you're going to notice that the major axis will be vertical. We're asked the same essential questions. Find the center, vertices, foci, and eccentricity of the ellipse with the given equation, then sketch its graph. Looking at this equation, the horizontal radius will be the square root of 16, which is 4, because that's the denominator of the x terms and its square root. The vertical radius will be the square root of 25, which is 5, because that's the value of the denominator of the y terms. Since the b value is greater than the a value, that tells us this time that the major axis is going to be vertical. Next, we can find the center of the ellipse by looking at the values being subtracted from x and y inside the parentheses. So since it's x plus 2, that will give us h equals negative 2 because you're subtracting negative 2 from the x. And since it's y minus 3, that means k equals 3. So our center point is going to be negative 2, 3. Before we look at the vertices and the foci, we will want to draw a quick sketch of this graph. The first point to plot is going to be the center at negative 2, 3. From there, we will use the horizontal and vertical radii to get the 4 key points needed to get a rough sketch of this graph. Since the horizontal radius is 4, we'll have points 4 units to the left and right of the center. Similarly, with a vertical radius of 5, we'll have 2 points plotted, one 5 units above the center and one 5 units below. Once we have these points, we can sketch our ellipse. Now we can see here that the major axis is going to be vertical. So the vertices are going to be those points on the ends that are 5 units above and below the center. These will be the points negative 2, 8 and negative 2, negative 2. Now, based on the values of A and B given, the major axis length is going to be 10 and the minor axis length is going to be 8. Now to find the foci, we will need to compute the value of C, which just like before, where we're going to take the semi-major axis squared minus the semi-minor axis squared. Then take the square root of that result, which will be 25 minus 16, which equals 9, and the square root of 9 will equal 3. So the foci will be 3 units above and below the center point, negative 2, 3. That's going to give you the points negative 2, 6 and negative 2, 0. Finally, we have the eccentricity computed as C divided by the length of the semi-major axis, which this time is the B value. So now our eccentricity is 3 over 5, or 3/5. Here in example 3, we're seeing a similar situation to what we did when we had the harder circle examples. The questions are the same, but the equation isn't written in the correct form for us to be able to quickly identify all of the key parts. So just like we did with circles, we are going to complete the square for both x and y. Now, just like we did before, we want to regroup the terms so that the x's are with the x's and the y's are with the y's. And we want to leave some space to insert some constants. So if this is our equation, x squared plus 2y squared minus 10x plus 8y plus 29 equals 0, we're going to move the two middle terms around, and so it's going to look like x squared minus 10x plus 2y squared plus 8y. And then we'll move the plus 29 to the other side of the equation to make this be equal to negative 29. Now, what makes this process different from dealing with circles is that the coefficients of the squared terms won't necessarily equal 1. So what we want to do is factor out the lead coefficients from those terms that are going to cause problems. Here, since the coefficient of y squared is 2, we'll factor out a 2 from the two y terms to now get 2 times the quantity y squared plus 4y inside the parentheses. Next, we will want to complete the square for both x and y. With the x terms, just like with circles, we'll take half of the negative 10, which is negative 5, and square that to get 25. You're going to add a 25 to complete the square on the left, and in order to keep the equation balanced, we need to add 25 to the right. Now, with the y terms, it's a little different. When completing the square for the y's, we want to leave the lead coefficient 2 out of it. So we'll take half of 4, which is 2, and 2 squared is 4, and add 4 inside the parentheses. So we'll have y squared plus 4y plus 4 inside the parentheses. However, remember, everything inside the parentheses is being multiplied by this 2 that's on the outside. So in order to keep the equation balanced, we don't want to add 4 to the right-hand side. We actually want to add 8 to the right-hand side because what I have is 2 times 4. From here, we want to factor each trinomial into perfect squares, then simplify the right-hand side, just like we did with circles. So we get x minus 5 quantity squared plus 2 times the quantity y plus 2 squared equals negative 29 plus 25 plus 8 will simplify to equal 4. So we're not quite done yet. We're actually very close, but not completely done. Our last step is going to be to get this into standard form, which requires that the equation equal 1 on the right side, not 4. So how are we going to do that? Well, we're going to divide everything in the equation by 4 and then reduce the fractions that we can see. So our final answer will have x minus 5 quantity squared over 4 plus y plus 2 squared over 2 equals 1. Now that the equation has been rewritten into standard form, we can start to identify all of the properties of the ellipse. The horizontal radius will be the square root of 4, which is 2, And the vertical radius will be the square root of 2, which as a decimal is approximately 1.414. The center will be at the point HK, recognizing that in this form we have x minus h and y minus k, that gives the center at 5, -2. The major axis is going to be horizontal because the horizontal radius is bigger than the vertical radius. So the vertices are going to be 2 units to either side of the center horizontally, which would place them at the points 7, -2 and 3, -2. The major axis length is 4, and the minor axis length will be 2 times the square root of 2. To find the foci, we'll take the difference of the two denominators, which gives us 4 minus 2 equals 2. So c equals the square root of 2. Since the major axis is horizontal, the foci will be the square root of 2 units to the left and to the right of center. So we see them here at 5 plus the square root of 2 comma -2, and 5 minus the square root of 2 comma -2. Finally, the eccentricity will be the c value, which is the square root of 2 divided by the length of the semi-major axis, which is 2. Lastly, we can sketch the graph like we did before. I'm not going to show it all step by step like I did in earlier slides, but here you see the ellipse with all of the key properties. The center is at 5, -2. The vertices are at 7, -2 and 3, -2. The co-vertices are at 5, comma, -2 plus or minus the square root of 2. The foci are at 5 plus or minus the square root of 2, comma, -2. Now, for example 4, I'd like for you to try this one on your own. What I recommend is that you pause the video long enough to work through all the steps just like we did in example 3. You'll want to rearrange the terms to put the x's and y's together, then factor out the lead coefficients so that we'll be able to complete the square more easily. Then leave some space to insert constants, complete the square for each term inside the parentheses, then add the value on the right to keep the equation balanced, keeping in mind you'll have to multiply the constants by that lead coefficient. Finally, once you've factored the expression, you'll want to divide both sides by whatever constant is left over on the right-hand side in order to get it to all equal 1. Then you can simplify the results. I'm going to pause here for a bit to let you get your chance to work through this one on your own. Okay, so here we go. So we're looking to regroup the terms of this equation to get the x's grouped together with the x's and the y's grouped together with the y's. So that gives us 9x squared plus 54x plus 4y squared minus 8y equals -49 after we move the 49 to the other side of the equation. Next, we'll factor out the lead coefficients of 9 in front of the x squared and 4 in front of the y squared to get what you see here. To complete the square, we need to look inside each set of parentheses and determine the constant that will allow that expression to factor into a perfect trinomial square. For the x's, you take half of the 6 to get 3, and 3 squared is 9. So while we can insert a 9 inside the parentheses, we need to remember that everything inside the parentheses is being multiplied by the 9 on the outside. So we don't want to add 9 to the other side. We actually want to add 81 to the right-hand side, 9 times 9. Similarly, we want to look at the y expression and see that the middle term is negative 2. Half of negative 2 is negative 1, and negative 1 squared is 1. This means to complete the square for y inside the parentheses, we want to add 1. However, everything inside the parentheses is being multiplied by the 4 on the outside. So to keep the equation balanced, we're going to have to add 4 to the right-hand side. Now, factoring each piece and simplifying on the right-hand side here, we have 9 times x plus 3 squared plus 4 times y minus 1 squared equals 36. So we're almost done, but not quite. We still need to get this expression to equal 1 on the right-hand side. So we're going to divide both sides of the equation by 36 and then reduce the fractions to get x plus 3 squared divided by 4 plus y minus 1 quantity squared divided by 9 equal to 1, which is our equation in standard form. Now that the equation has been rewritten in a standard form, we can identify all the properties of the ellipse. The horizontal radius will be the square root of 4, which is 2, and the vertical radius will be the square root of 9, which is 3. The center will be at hk, and again, recognizing it's x minus h and y minus k, that gives us the center at negative 3, 1, because it's x minus negative 3 and y minus positive 1. The major axis this time is vertical because the vertical radius is bigger than the horizontal radius. So the vertices are going to be 3 units above and 3 units below the center vertically, which will place them at the points negative 3, 4 and negative 3, negative 2. The major axis length is going to be 6, which is 2 times 3, and the minor axis length will be 4, which is 2 times 2. To find the foci, we take the difference of the two denominators, but we need to subtract them in a way that makes the difference come out positive. This gives us 9 minus 4, which equals 5. So C will be the square root of 5. Since the major axis is vertical, the foci will be the square root of 5 units above and below the center. Finally, the eccentricity will be the c value, or the square root of 5, divided by the length of the semi-major axis, which is 3. At this point, we now have enough information to sketch our ellipse. Again, I'm not going to show it all step by step, but here what you see is the ellipse with all the key properties. The center is at negative 3, 1. The vertices are at negative 3, 4, and negative 3, negative 2. The co-vertices, if we went left and right 2 from center, are at negative 1, 1 and negative 5, 1. The foci are the square root of 5 units above and below the center, which are at negative 3, 1 plus the square root of 5, and negative 3, 1 minus the square root of 5. This next example is one where you're given the properties of the ellipse and you need to find the equation. Here's the question. Find the equation of an ellipse with vertices at the points 0, negative 6, and 0, 6, and foci at 0, negative 4, and 0, 4. So this one is going to take a bit of thought. We know the standard form of the equation. That we have here is x minus h quantity squared over a squared and y minus k quantity squared over b squared equals 1. The question is, How much do we know already, and what will we still need to do? Well, in our standard form, we know that h and k are supposed to represent the coordinates of the center point, and a and b will be the horizontal and vertical radii respectively. X and Y are arbitrary values that represent points on the graph of the ellipse. So our goal is going to be to try to use what we know to figure out what the values of H, K, A, and B are going to be. So what do we know so far? Well, we know where the vertices are. We know where the foci are. So we should be able to get to the center point, because the center point will always be the midpoint between the vertices or the midpoint between the foci. Either way, if you look for that midpoint, you're going to find it to be the origin 0, 0. So we can start by inserting the h and k value we just realized into our equation. Now our equation will look like x minus 0 quantity squared over a squared plus y minus 0 quantity squared over b squared equals 1. Next, if the vertices are at 0, 6 and 0, negative 6, then the vertical radius b has to equal 6, and the major axis is going to be the vertical one. So now our equation will look like x minus 0 squared over a squared plus y minus 0 squared over 6 squared equals 1. All we have left to do is figure out what is the value for a. Well, the only other information we're given is the location of the focal points at 0, 4 and 0, negative 4. We know that the focal points are always C units from the center point. So that means C must equal 4. Finally, we can solve for that missing value A by using the equation C squared equals B squared minus A squared. We know it has to go that way in this formula because we always take the semi-major axis squared minus the semi-minor axis squared to get c squared. The vertical axis is the major axis, so we have to write this as b squared minus a squared. So we have 4 squared equals 6 squared minus a squared. Then expanding, we have 16 equals 36 minus a squared. So rearranging the terms will give us a squared equals 20. Plugging that into our standard form and simplifying the minus 0 inside each parentheses gives us x squared over 20 plus y squared over 36 equals 1, and that will be our final answer. So that wraps up my presentation on ellipses. Most of what was covered here should get you through both the 11.2 material and the 11.4 questions tied to ellipses. As a reminder, the biggest difference between the two sections is that all the ellipse problems for section 11.2 have their center at the origin 0, 0, while the ellipses have their centers at hk, some other point than the origin. But the processes and procedures are pretty much going to be the same. Here are the problem challenge problems for the two sections which cover ellipses. As a reminder, I'll be taking questions on these particular problems during one of the ORT sessions this week. These problems will not be graded, but it is in your best interest to do these problems to prepare you for both the homework and the first quest. All the answers to these problems should be in the back of the book, which should make things go more smoothly. As a final reminder, if you came up with any questions about this material during your review of this lecture and you want to pose them before our next class, you can always email them to me at miaresj@d2l.lcc.edu, or you can post them to the discussion board under the general questions and items to share forum. Thanks for watching, and we'll talk to you soon.